What's up, my stats stars? Michael Princhak here, ready. Good luck on the AP Stats exam tomorrow, everybody. So I really just want this to be kind of about an hour-long video to just answer any questions you guys have. So I'm going to grab some comments that you guys are making, some of the appropriate ones, and bring them to the screen here so we could talk. But just a couple general things. Obviously, good luck. Hope you guys do well. Remember, you got 90 minutes for 40 multiple choice questions. A lot of kids want to know, how many questions do I have to get right to get a 5? To pass the exam, I always tell my students 20. If you can get half of them right, you're definitely on track to pass the exam, getting a 3, 4, or 5. If you could get 25 to 30, you're probably closer to that 4 range. And if you could get above 30, you're probably going to be way into that 5 range. And then on the FRQs, number 6, the investigative task is, weighted more. But don't stress about that at all. I always tell my students, do 1, 2, 3, 4, and 5 first. Collect as many points as you can on those 5 questions, and then do number 6. If you have 5 minutes left, that's great. If you got 25 minutes left, that's awesome. But some teachers will say to do number 6 first. I don't like doing that because some kids will get infatuated with it, and then they're just stuck on it, and they end up spending a half an hour or more on it, and then they don't even get it right. They just waste their time. But one trend I have seen over the last couple of years is that number 6 has gotten easier. It's not gotten harder. It's gotten easier. So the international exam last year, it was really easy. They had you ranking numbers, just putting numbers in order, and then they were following some formulas. They gave you some new formulas. All you had to do was plug numbers in. It was not hard at all. So don't panic about number 6. Sometimes it is a little bit more difficult, but lately I've been seeing some really easy ones. And if you can even just get half credit on those FRQs, maybe you don't even get to number 6, you just get half credit on 1, 2, 3, 4, and 5, you're definitely on track to pass the exam. Maybe get 1 or 2 right, and then the other ones you get half credit, then you're on track to get a 4 or 5 for sure. So don't panic and don't say you're cooked, because you're not. You're going to do great. All right, so let's get some comments from you guys, see if anybody has any questions here. They want to ask. What are some comments here, Patrick? Give me some. Matched pairs are too simple. This is a very, very common question. So the idea of a matched pair is that the data is paired data. So they might present it as there's 2 rows or 2 columns of data, but it's not. You got to read the question. There was 1 sample. It was either 1 sample of, let's say, 30 people, but everybody was measured twice. There was a before measurement and an after measurement. Or I've seen a question a couple years ago. They had 10 pieces of meat and they were testing them for E. coli, and they did 2 different tests. So they had 10 pieces of meat. They did test A, they did test B. So they had these 2 numbers for each individual. And then what you care about in that case is the difference between those values. So again, you got to read the problem to get that sense it's dealing with matched data. Or maybe you have pairs of people put together and they're very, very similar, because that's the whole idea of a matched pairs experiment, is these 2 people that are very, very similar together. And then one gets A, one gets B. And then what you're doing is looking at the differences between those. Whereas a 2 sample test, there is clearly 2 separate samples. You have 2 groups of people. This group of 50 people do treatment A. This different group of 50 people do treatment B. And then you have 2 totally separate groups. Or you just have 2 samples. You have a sample of girls versus a sample of boys. And you have, the mean amount of time girls spend on homework versus the mean amount of time boys spend on homework. But it's very clear there's 2 separate samples. So that's how you will know that the difference between a 2 sample test versus a matched pairs test. Definitely a lot of multiple choice questions will give you a scenario and you have to choose. Is it a 1 sample Z test, 2 sample T test, matched pair test, chi-square test? So you got to make sure you understand those different tests for that. And every now and then, you never know if it's going to be this year, there could be a matched pairs test. Most kids are like, please don't ever give a matched pairs test on the FRQs. You never know. But here's the good news. If you accidentally treat it as a 2 sample test, sometimes you can actually still get full credit. Because as long as all of your work is correct, even though you chose the wrong test, they'll still probably, as long as everything's nice and good, you can still potentially get 4 points on that question. All right, what else we got? What is the one where if it fails independence, you can still do it? Boy, I don't know the answer to that. I maybe need a little bit more context there. But basically, just to answer that one kind of real quick, the independence is the under 10% condition. You only have to check that under 10% condition when you are sampling. If you're doing an experiment when you got 50 volunteers and 25 are going to do this and 25 are going to do that, you don't have to check that 10% condition because they're already independent. Like these people are doing this, these people are doing this. They're already independent. They're two different groups. You're not sampling from the population. That's when you have to check that 10% condition. All right, what was the next one there? Anyone have a good tip for type 1-2 error? Honestly, my own students ask me this, and I don't have a good answer. I wish I had some good kind of saying for it. Some teachers may, I don't know. But I always think of it like this. Here's how I remember it. I don't know if it'll help or not. But when you write your null and alternative hypothesis, you put the null hypothesis first, and then the alternative hypothesis second. So type 1 error, the null hypothesis is true because it's first, right? Type 1 first. So the null hypothesis is true. But there's a mistake. There's an error. They call it an error for a reason. And the error is that we reject it and we go with the alternative when the null was true. And the alternative hypothesis is written second. So a type 2 error is when the alternative hypothesis is what's true, but it's called an error for a reason. We fail to reject the null. So we keep a null that's wrong and we go and we don't go with the true alternative. So I don't know if that'll help you or not, but that's how I kind of explain it. All right, what else? What happens if condition fails on a test? Okay, great question. A lot of kids ask me this. On an FRQ, that will never happen. I'm telling you right now, they're never going to try to trick you. They're never going to give you an FRQ where it's like a trick FRQ, and at the end, you should have just written, ha, 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 can't do it. Conditions didn't pass. I promise you on an FRQ, if you're asked to do an inference procedure, which you will be guaranteed, it will work out. The conditions will pass. So just make sure you know what they are. Now, I have seen multiple choice questions where the question is which one of the conditions fails, and then that's where it's kind of alerting to you. Okay, I got to think about those conditions because one of them is going to fail here. All right, what else? How do we identify which statistical inference test we should use? All right, that's a great question that would take me, to fully explain all of it would take me a long time. So I actually want to say, and I don't know how easy it is for me to put a link up. I have a YouTube video that goes over exactly that. I'm going to try to see if I can grab it real quick and send it to you. I have a YouTube video called Inference Procedures, the Ultimate Guide to Inference. Let me see if I can bring this into the chat real quick. This video is awesome. It's I think it's one of my better videos, and it doesn't even have a ton of views, but I think it's fantastic. I'm going to try to throw it in the chat right now, see if this works. Yeah, there it is. I just threw it in the chat. So in this video, I explain all the different inference procedures and how you should know, based on reading the problem, which procedure do I do this and when do I do that. So that video will really help you. And that video also goes over 2 acronyms that I didn't create. So, I'm not trying to take credit for this. But if you're asked to do a confidence interval, PANIC, PANIC, is the acronym for what you have to remember to do. P stands for parameters. You have to define the parameter you're looking for. A stands for assumptions, which are the conditions. N is to name it. I'm doing a 1 sample T interval for a population mean amount of time kids spend on homework. I stands for the interval. If you use your calculator, you don't even have to show work. Use your calculator, get the interval, and then C is to give your conclusion. For inference tests, a significance test, PHANTOM, PHANTOM, is the acronym. P stands for, again, name your parameters, to describe what it is the problem's dealing with. H is the hypotheses. Let me try to remember. A is for the assumptions again, the conditions. PHAN, name the procedure, a 2-sample Z test or a 2-sample T test. And then we have the test statistic and obtain your p-value. That's what the O stands for. And then again, no work. You can have your calculator do all that for you. And then the M is make a conclusion, make a decision based on the p-value. All right, so what else? What is the difference between standard deviation, standard error, and variance? Great question. So first, variance is just standard deviation squared. It's really that simple. So if the standard deviation of the population is 5, 25 is your variance, or just 5 squared. That's your variance. Really that simple. Now, standard error, I tell my students it's the twin brother of standard deviation. It's the exact same formula. It's just replacing P with P hat, or the standard deviation of the population with the standard deviation of your sample. So let me actually better explain that real quick by showing you the formula sheet. So give me 1 second to share my screen so I can bring up this formula sheet here. Hopefully this will work. There we go. So if you look at the second page of the formula sheet, and again, this will all be digital this year, right? So there'll be a little box, some multiple choice or FRQs. You could click on this. So this first box is for proportions. And you'll see 2 rows, one for a single proportion and one for 2 proportions. And Patrick, can you take that comment away real quick so they can see more of the screen? And what you see is the first column is the mean of the sampling distribution. The second column is the standard deviation, sigma. And then the third column is standard error. And notice, like, for example, this very first row, the only difference between standard deviation and standard error is we don't know the population proportion. We only know the sample proportion p hats. The p's turned to p hats, that makes a standard error. Same thing with the difference between 2 samples. The p's turned into p hats. And then if we scroll down to here, this is for means. First column, the mean of the sampling distribution for means. Standard deviation, we see sigma. And then the standard error is the final column there. And again, notice the only difference is we don't know sigma, the standard deviation of the population. All we know is S, the standard deviation of our sample. And that's when we use standard error. Standard error is going to primarily be used in confidence intervals for sure, but it also gets used in tests as well. And again, if you know what you're doing, all you got to do is look on this formula sheet here to get the right formulas. All right. I'm going to stop sharing my screen there. Okay, what else? More questions. Could you go over power, definition, how to increase? Okay, great question. Yeah, I think I have a video over power as well. So, if I'm going to try to answer as many questions as I can tonight, but only have limited time. But if you go to my YouTube channel, kind of like in the middle of my home screen, there's a little magnifying glass. You can actually search just my channel. So if you type in like power, you could probably find at least 2 or 3 videos that cover power. But power is the probability of correctly identifying a true alternative hypothesis. So if in reality the alternative hypothesis is true, power is the probability that you recognize that. You will not be asked in the AP exam to calculate power. You're never going to have to find the actual answer. It's more of a theory thing that you need to worry about. Maybe in college you'll figure out power, but just knowing the definition right now. Now, how to increase it is going to be a very common question, because power is a good thing. Because if the alternative is true, we want to see that. We want to recognize that. We want to conclude that. So 3 ways to get more power. Number 1, bigger sample size. Right? Just think about it. If you're trying to find the true weight of frogs, if you look at a sample of 5 frogs, you might be way off. If you look at a sample of 1,000 frogs, you're going to be way closer to the truth. So bigger sample will always give you more power. Second is increase alpha. Remember, alpha is your level, your percentage of rejection, right? So we could use 1% or 5%. Well, if we use 5% versus 1%, we have a bigger area for rejection. So, a p-value of 0.04 would cause us to reject with 0.05, but at 0.01, we wouldn't, right? So it gives us more room to reject. So if we go from 1% to 5%, we technically have more power because we have more room to reject. And if we're supposed to reject because the alternative is true, then that would do good, right? Or we can even go up to 10% for alpha, giving us 10% room to reject. And if that's what we're supposed to do, then that's going to give us more power. Now, the third way to get more power is like a little bit out of our control, but it's if the truth is further from the null. So let's say the null is that the true mean of the population is 20. Well, if the actual mean, the real mean is like 50, well, then you're going to have more power, because if the real mean is 50, that's way far from 20. And if the real mean's 50, we should definitely reject 20. We should be like, no, 20 is not right. The mean's 50. So it's really high. Excuse me. So the further the truth is from your null, the more power you have. Versus if the truth is 21, well, 21 is pretty close to 20, so maybe, 21 is the truth. We should reject the null because the truth is 21, but 21 is so close, we might not see that in a sample. So we have less power. So, all right, hopefully that answers questions about power. What else? What's the difference between a t-test and z-test, and how do we determine that in a problem? All right. My biggest concern with this is a lot of kids, they depend on their calculators so much that they don't understand what their calculator is saying, especially the TI-84. So let's keep this as simple as possible. And, without trying to explain too much. If you are working with a problem that deals with proportions, whether it be a single proportion, the percentage of people who vote yes on an upcoming election, or the difference of two proportions, the proportion of people who vote yes in Canada versus the proportion of people who vote yes in Mexico, you're going to be using a z-test, right? Because when you're working with proportions, you're always working with z-scores. Done. Simple. When you work with means, we usually, in AP statistics, we only ever know the standard deviation of our sample. And that's why William Gossett invented the t-distribution, because it's more accurate when you only know the standard deviation of your sample, which is only a problem with means. So when we're working with means, whether it's a test for mean, like, hey, I heard that the true height of people in Poland is 70 inches, and we think it's less. Whatever, you're working with means, right? The problem says means, then that's going to be a t-test. Or if it's a difference between two means, that's going to be a t-test. Now, theoretically, you could use a z-test instead of a t-test, but you would need to know the standard deviation of the population. And in AP statistics, that's never going to happen. So try to keep it simple. If your problem is based with proportions, use z-tests or z-intervals. If the problem is based on means, you're going to do t-tests or t-intervals. So I know I'm not getting to all the technicalities of it all right there, but at least try to make it as simple as I can the day before the exam. All right, what else? Large counts, conditions, and when to use central limit theorem. Fantastic. So let's talk about the three conditions that are very popular. First condition is that your sample's got to be random to avoid bias. That's easy. Second is that 10% condition that allows us to assume independence. Our sample size has to be less than 10% of the population, so we assume independence. Okay, the third condition, very generically, is called the large counts condition, or I call it the big enough condition, right? Everybody says something different. The large counts condition, big enough condition. Now, that condition changes depending on the problem. If you're working with a proportion-based problem, you have to check that you have 10 or more successes and 10 or more failures in your sample, expected in your sample. That way you meet the big enough or the large counts condition. Easy. If you're working with means, there are three different ways to meet the large counts or the big enough condition. First, if your population that you're sampling from is normal, any sample size will do, even a sample size of 1, as long as your population is normal. If your sample size is 30 or larger, that's when the central limit theorem comes in and says, hey, your sample is large enough. The sampling distribution is guaranteed to be normal. Even if your population is not normal, who cares? Because you're 30 or larger, central limit theorem says the sampling distribution for means will be normal. So, when you ask that question, they're almost kind of one and the same. The central limit theorem is needed in a situation where the population is unknown, but your sample is more than 30, then you're good to go. Now, the third way to meet the large counts condition when you're working with means is that if your sample is less than 30, so you can't use the central limit theorem, and your population is not normal, then what you have to do is you have to check your data, quick histogram, quick box plot, and make sure that there's no major outliers and no major skewness. So hopefully I answered that question. All right, what do we got? When great question. There really is no answer to that. Most questions on the FRQ, like an FRQ, will tell you use 0.01 or use 0.05. If you use 1%, you're more strict. You're being more strict. But if you use 5%, you're giving yourself more power, as I talked about earlier. But on the FRQs, they will tell you what to use. And if for some reason they don't, you get a pick. They don't like it when there's multiple answers. So if the p-value is like 0.03, well, then you could have two different answers based on your alpha level. So on the AP exam, they usually end up getting a really, really low p-value where you're clearly going to reject an all, or a really, really big p-value where you're clearly going to fail to reject an all. And then even on multiple choice, multiple choice, there has to be a right answer. So they will give you your alpha level. What else? Can you go over P combined? Okay. So the only time you ever have to worry about this P hat combined crap is on a 2-sample z-test for the difference between two population proportions. So you got a sample proportion of boys and a sample proportion of girls, and you're looking at the percentage that like chocolate ice cream. Like what percentage of girls like chocolate ice cream versus what percentage of boys like chocolate ice cream. So when you do this, the null is, of course, there's no difference. P for girls is equal to P for boys. They're the same. And the alternative is, no, I think girls are a higher percentage of girls like chocolate ice cream. So P girls is larger than P boys. Okay, awesome. But when you go and create your standard error, you have to assume that there's no difference because that's the null. There's no difference. So only in this test do you need to do that combining. So basically you take all of your kids, boys, girls, who cares, put them all together and get one P hat. Now let me show you on the formula sheet one more time here. So here we go. So on the formula sheet, right here is where we have that formula. So in this far right box here. So notice it says when P1 equals P2, which is only in the only time you're ever going to assume that P1 equals P2, in our case, PG equals PB, is in a 2-sample z-test for the difference between two population proportions. And this is when you use P hat combined. That's what they call P hat C. So you're taking your two samples in the denominator together, boys, girls, all together, and then all of the successes, everybody that likes chocolate ice cream, boys, girls, add them all together to get one P hat combined, and then you use it here in both of that, inside there. Now, basically what they did was they just factored out because they're both numerator and you could distribute, so the numerators would be the same, but they just factored out. But that's where you get that idea. So that's the only time you have to do it. When you are doing an interval, for a, hold on a second here, I'm trying to get there we go. When you're doing a interval for the difference between two population proportions, you do not need P hat combined because there is no assumption there. So hopefully I answered that. That's a, if you're like, I have no idea what you just said, well, then you probably didn't learn any of that during class or you never heard it all. So, but if you vaguely remember learning that, then hopefully that makes sense to you. But when we're working with means, you never have to worry about combining. All right, what else? Types of sampling bias. Yeah, for sure. Great question. So the different types of sampling bias. So using volunteers, that always produces a bias. It's called volunteer bias. Convenience bias, using a sample that's out of convenience, like, I'm just going to grab the first 10 people I see on the street because it's easy for me. That's bias. Now, those are kind of under an umbrella called selection bias. Selection bias is anything that's wrong with your selection process. Using volunteers, doing something out of convenience, purposely undercovering or purposely overcoveraging people. Like those are classic examples of selection bias. Like anything that caused the selection was bad. It wasn't random. Let's put it that way. Then we have response bias. Response bias is you might have the best sample in the world, like the most 1,000 random people in the world, beautiful sample, but they lie to you. They don't give you an accurate response for any reason. Maybe it's because they felt pressured. Maybe it's the wording of the question. Maybe it was the dentist that asked them, do you floss? And you're going, oh yeah, I floss every day. Yeah, sure I do. Maybe it's because they had to put their name on the survey. They felt uncomfortable with that. Anything that causes, even if you have a broken scale, like let's say you're weighing, you're doing an experiment with raccoons and you're weighing raccoons and the scale that you're using for the raccoons is broken. Well, they lie to you. The scale lied to you. That's response bias. Then we have non-response bias. Sorry, I'm battling allergies right now, so I keep coughing. But non-response bias is when, again, you get this great, beautiful sample, but 50 people chose not to respond to you. And that matters because maybe the reason they're not responding is something important that matters to the problem. And remember, when you are sampling, you want to get everybody's opinions. That way you have a mix of opinions and you're closer to the truth, right? That's the whole point of sampling. And if you allow those 50 people to not respond, well, then maybe they're not responding for an important reason that matters to what you're investigating. If you allow them to not respond, you never learn about that. And then hence you never get an accurate representation of the population. So, all right, hopefully I answered that one. What else? So, hi. So I was studying binomial distribution and this symbol came up No idea how that relates because it was numbers, but it wasn't your N and X on the top and bottom of it. So that symbol is the Greek letter sigma for summation. Basically means add them all together. With the binomial distribution, you should not ever need that symbol. Let me show you the formula sheet real quick, and then we could talk about it as well. And if you could clarify that question, I'm trying to answer as best I can. But for example, if we look at the formula for the mean, X bar, we notice that sigma symbol, because that means add up all of your values and divide by how many you have, you get your mean. Simple, right? We also see that right here with the discrete. So if you have a discrete random variable, to find the mean, you multiply each outcome, X, by its probability, P, and then you add up all of those values. That's how you get the mean of a discrete random variable. But if you notice this row here for the binomial distribution, I don't see that sigma there anywhere. So like you mentioned that N over X, so that's part of the formula to find the probability. So we have N is, how many are in your sample divided by X, how many successes you want to have. So that symbol should not be popping up anywhere when it comes to binomial distribution. All right. What else do we got here? In computer regression, and by the way, that last person, thank you for the donation. I appreciate that. But so if you can better word that question or a different question, I would love to answer it for that donation. All right, in computer regression output, is the given p-value one-sided or two-sided? Oh boy, you're really testing me here. It's two-sided in a computer regression output. So the null would be that the slope equals 0, which means that there is no slope, right? And then the alternative could be greater than, less than, or not equal to. But I do believe that it is not equal to, which means it's double-sided. So it would be when you don't even care if there's a positive slope or negative slope, you just care that there is a slope. But that's a very rare thing to come up on the AP exam, and may happen every now and then, but that's a great question. So hopefully I answered that one. What's the difference between normal PDF and normal CDF? Great question. You will never, ever in AP statistics use normal PDF. Never. It's not worth me wasting 10 minutes trying to explain what it does. You're never going to use it. You're going to use normal CDF. Normal CDF takes that normal model, and it could look above a z-score. It could look below a z-score. I don't even know if I'm moving my hands right. But it could look above or it could look below to get you proportion. It could also look in between two z-scores. And if you have a NumWorks calculator, the greatest calculator to ever be made in the history of the universe, there is a there is a normal app. There's a distributions app. And in that distributions app is the normal distribution. And you could look above, below, or in between really easily as well. So hopefully that answers that question. All right, what else? What is a discrete random variable? All right, fantastic. So a random variable is any random phenomena where the outcome is a number, right? So anything that's random and the outcome is a number, like how long am I going to take a shower tonight? I don't know, 30 seconds, 31 seconds, 32 seconds, 45 seconds, 99 seconds, so 526 seconds. How many, I'm going to shoot 10 free throws. How many do I make? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's a discrete variable, right? Or that's a random variable. The outcome is a number. Simple. A discrete means that it's typically going to be a whole number. And, some people could argue that it's a little bit more than that. But if you could make a list of all the outcomes. For example, I'm going to shoot 10 free throws. I can make a list of all the outcomes. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. Made my list. That's discrete. Or, I sell T-shirts. True story. I used to have a T-shirt company. It fell through. Long story. But anyway, I could sell 5, 4, 3, 2, 1, or 0 T-shirts on any given day. That's a discrete random variable. The outcome was a number. A continuous random variable is when the outcome is measurable and you think decimals, so that the outcomes are just too many. Like how long I could take a shower tonight. That's continuous because it, first off, every second, it's just an endless list of numbers, right? 1, 2, 3, 4, 5, 6, 7, all the way up to 1,000 seconds. But then you also have decimals, right? You're measuring it. I get a good stopwatch. It could say, 123.456 seconds. Now we got literally infinite outcomes. So that's continuous. So discrete, on the AP exam, I've seen questions like, hey, I think one of my videos, I had a question like this. You have a horse and you're going to enter that horse into 2 races. And you say, how many wins could the horse get? Well, the horse could lose both. That'd be 0. It could win both. That'd be 2 wins. Or it could win one of the races. That'd be 1. So 0, 1, and 2 are your outcomes. That's a discrete random variable. All right, what else? Different types of blocking. Yes. So I'm a little confused by that question, different types of blocking. There really is only one type of blocking. So blocking is done in an experiment. And let's say we're doing an experiment. We want to see if a new pill helps you lose weight. I'm just trying to think of something simple. So, a completely randomized design. You get 1,000 people, 500 take the pill, 500 take a placebo, done, easy. But if you are like, man, there's a confounding variable, diet. Like diet matters so much. Like, yes, we hope the pill helps you lose weight, but diet helps you lose weight too. So this is where we say, okay, we're first going to block the people, not randomly, but by their diet. So we got maybe good diet, medium diet, like okay diet, and then a bad diet. And that's just by asking the people, surveying them, getting some information from them. Then we basically run a mini experiment in each one of those blocks. So of the people with bad diets, half get the pill, half get the placebo. Good diet, half get the pill, half get the placebo. Okay diet, half get the pill, half get the placebo. So what we're doing is we're guaranteeing that in that pill group, we got good diets, bad diets, okay diets. In the placebo group, we're guaranteeing good diets, bad diets, and okay diets. That way, in our 2 groups, pill, placebo, we have a complete nice mix. It's not just up to randomness, because we live up to randomness, we might get all the bad diet people in one group. Well, if we do it by blocking, it guarantees we don't have that happen. So blocking is very much like stratifying, but in an experiment. Stratifying is when you're not doing an experiment, you're just sampling. Like, hey, I want to make sure I get, a whole bunch of different grade levels. I'm going to take a couple freshmen, a couple sophomores, a couple juniors, a couple seniors. That's stratifying, but it's very similar to blocking, but blocking is the term we use for experiments. All right, what else? Are there other ways to influence the width of a confidence interval besides changing the level? Yes. Great question. Let me share my screen. And I don't use StreamYard more than a couple times a year, so sorry if I'm not too great at this. So just give me 1 second to share my screen here. And I don't even know if I'm doing it. Hold on a second. No. I don't even know if I'm sharing my screen right now or not. No, I don't think I am. Why aren't I sharing my screen? Okay, share screen. There we go. Okay. Sorry about this. I am terrible at this. Okay, there. Hopefully you can see my screen now. All right, so let's talk about this. So let's just say we're doing one for means, right? So we have our sample mean, X bar, plus or minus a T star, which is, again, based on your level of confidence, multiplied by the standard deviation of your sample, divided by the square root of that. So you mentioned that one way to change the interval width is to change your T star, right? 99% confidence can be wider, 90% confidence can be more narrow. Okay, you understood that. The other thing you could do is change these 2 numbers, right? For example, bigger sample size. A bigger sample size is going to make your interval smaller or more narrow. Why? Because you divide by n. Yes, it's in a square root, but you're dividing by it. And what happens when you divide by a bigger number? You get smaller. So bigger sample size will make your interval smaller, which means it's more accurate, which is a good thing, right? Also standard deviation. Now, standard deviation is in the numerator. So if we want a smaller interval, we want a smaller standard deviation. But think about that. A smaller standard deviation means your data is more accurate, and more accurate data should produce a more accurate interval. A bigger standard deviation, because it's in the numerator, will make your interval bigger. But a bigger standard deviation means that you're less accurate, which means you're going to have a less accurate interval. So hopefully that makes sense. It should, I think. What else? What is the difference between a sampling distribution and a simulation? Great question. So a simulation, I honestly don't even teach them anymore. Hopefully that's bad. It's in the curriculum, but I have not seen a simulation come up on the exam in a long time. But here's what I think you're kind of getting at. The definition of a sampling distribution is a distribution of all possible sample statistics of a particular sample size taken from a particular population. So imagine we have a population of people, and we're going to look at samples of size 50, and we're going to look at their mean weight. Well, a true sampling distribution will have every single possible sample mean weight from 50 people taken from that population. That, I mean, if you think about just the state of Pennsylvania, there are bazillions of samples of size 50. You know, if one person changes, it's a whole new sample. Maybe 49 say the same, but one person's new, whole new sample. So there are so many different sample means. It's literally, there's billions of them. I can't even say there's so many, right? But a true sampling distribution has all of them. And that's why we really can't make it, but we model it with a normal model. We know that most are going to be near the truth, very few on the high end, very few on the low end. But what we do a lot of times comes up on the AP stats is, hey, let's just look at 1,000 samples. Let's just simulate. That's what you're kind of saying there, simulation. Let's just look at 1,000 samples. We don't got time to look at all of them because there's billions of them. So let's just look at 1,000. So we get 1,000 samples of 50. Now, is that a true sampling distribution? Nope. But it's close. Now you say, wait a minute, 1,000 is close to 1 billion? No, it's not. You're right. But the idea is, this is the cool thing about sampling distributions, even if we just simulate 1,000 samples, it's already going to start to show us the 3 characteristics that we know to be true. It's going to be normal. We're going to see a lot of samples in the middle, near the truth. We're going to see very few high samples, very few low samples, and the mean's going to be in the middle, and there's going to be a standard deviation. So, and that does come up a lot of times on the AP exam, especially with question number 6, because maybe they say, hey, let's look at medians, not means, not proportions, look at medians, and let's look at a simulation of a bunch of different medians. And guess what? It's going to look normal as well. So hopefully I answered that question. I feel like I didn't, but hopefully I did. All right. Can you explain, Patrick, I also saw that somebody donated some money. So let's make sure we get their question up here soon too. Can you explain independent events, for example, D or E or D and E? Okay, so first, let me show you the formula sheet again. Let me try to explain this. Share my screen. There we go. Okay, so on the very front page right here in underneath probability and distribution, right here, this is the addition formula. Now, I hate that they don't use the word or and, but the U looking symbol, that's or. And then on the far right, the upside down U is the and. Now, or, A or B means A or B or both. And means both of them, right? Overlap. You got to have both. So, and connecting it to independence, which you asked about, if 2 events are independent, then what we know is that A times B equals the probability of A and B. But that is only true if you're independent. So if you read a question that says, hey, the 2 events A and B are independent, then to find the probability of A and B, just multiply A times B. Now, what if they're not independent? Well, you could still multiply them. You just can't, you have to think conditionally. You have to think, okay, I got A and I got the B, but does the probability of B change because of A? That's what it means when you're not independent. And then you can multiply those outcomes. So hopefully I answered that question. Sorry if I didn't. But if I got 4 videos on my YouTube channel, they're pretty new videos. Each one has 10 multiple choice questions. You could view the question, pause the video, and try the question out. If you watch part 4, all 10 questions deal with probability. There's 2 or 3 questions that deal with probability of A and B or A or B. So you might want to check that out. It can definitely help you. Can you go over what conditions are needed for all 3 chi-squared tests? All right, they're the same. They're the same. So the 3 conditions for chi-squared tests: random sample. Sample must be random to avoid bias. Second, the sample must be under 10% of the population, because when you are sampling from a population, we have to make sure we can assume independence. So we need to be under 10% of the population. And then the third condition for chi-squared tests is that you must have 5 or more expected counts in each category. So if you have one categorical variable with multiple categories, blue fish, red fish, green fish, yellow fish, purple fish, black fish, brown fish, whatever, every one of the expected counts must be 5 or more. If you have a 2-way table, maybe you have color of fish and gender of fish, then every one of those cells must have 5 or more expected counts in it. So those are the conditions for the chi-square test. All right, what else? Can you explain how to interpret a p-value? Yes, as easy as I can, right? I can spend 3 hours on this, but a p-value is the probability of your sample statistic occurring or more extreme. So to me, a picture is worth 1,000 words. So I'm going to pull up my screen again here. I'm so sorry I'm slow with this. I'm just not used to doing it very often. All right. So again, a p-value is the probability of your sample statistic occurring or more extreme on the assumption that the null is true. So let's just say we have a sampling distribution. Sorry for my terrible drawing here. And right smack dab in the middle is the null, right? This is what the null hypothesis, this is what we believe the true proportion to be, right? So, maybe we read that 25% of people recycle on a daily basis. So that's what we assume to be true right smack in the middle. But our sample comes back 37%. So if we say, okay, so where does our sample fall on the sampling distribution? Well, obviously 37 is above 25, but how far above 25 is it? So let's just say it's only a little bit above, like maybe right here, right? So the p-value would be the probability of that sample occurring, 37%, or more extreme. Now, since it's already higher, we would look higher above it, right? Or more extreme would be even higher. And that's pretty likely. Like, that's not weird. There's a lot of samples that come back 37% or higher. That's not weird. So in that case, we would have a big p-value and we would fail to reject a null. We do not have enough evidence to say that more than 25% of people, recycle. Yes, 37 is higher than 25, but it's not that much higher. Verse, let's do this again here. So we have our sampling distribution, or right smack dab in the middle is the 25% that we assume to be true. But maybe this time, for whatever reason, the 37% is way over here. That was our p hat, way over there. Well, now, that's rare. That's very unlikely. The p-value is the probability that, that sample proportion of 37% occurs or more extreme. And in this case, it's very, very rare, very, very unlikely, but it did occur. So what's the explanation? Well, this must be wrong and the truth must be higher, because if the truth was higher, like maybe the truth was right here, then all of a sudden our sampling distribution, the 37% would not be weird. So that's why when we have a very low p-value, we reject the null and go with the alternative. So I don't know if I answered your question. I mean, I feel like I answered your question, but hopefully I did in terms of interpreting the p-value. But, one more thing about that. On an FRQ, I've not really seen in a while them asking you to interpret the p-value, but definitely can come up on a multiple choice question where you got to choose the one that interprets it the best. All right, we got about 15 more minutes left. Okay, can you help me choose the right procedure on 4 CFRQs? I have a hard time identifying what an H should be if it's difference. Okay, so one more time, real quick. I'm going to direct you, and I'll answer your questions best I can. But I'm going to direct you to a video I have. I'm going to get the link one more time. I'm going to share it right now in the chat. This is a link to a video I have that covers all the different inference procedures, and it kind of goes through what's needed and kind of how to know the difference between them. Now, I don't know. You say 4C FRQs. I don't know what you mean by on the 4C FRQs. I'm not sure what you mean by that. But one of the FRQs is going to be inference, guaranteed. I wish I knew what it was because I would tell you right now, and you'd all study that different procedure and you'd get it right. Could be an interval, could be a test. Who knows? Proportions, 2 proportions, means, 1, 2, match pair. So, in terms of the hypotheses, if you're working with 2, right, there's clearly 2 samples. The null is that they're the same. The 2 proportions are the same. The 2 means are the same. P equals P, mu equals mu. The alternative, you got to read the question. Does it say, oh, we think the proportion of boys who like chocolate is more than the proportion of girls? Well, then you'd have PB greater than PG. But don't forget to define what PB and PG are, right? That's number 1 when you talk about panic or phantom. Number 1 is define your parameters. Or maybe the question says, we don't even care if boys are more than girls or girls are more than boys or boys are less than girls. We just care that they're different. That's when you choose a not equal to side for your alternative hypothesis. So watch that video. It really will help for sure explain that, I think. All right, what else? Okay. Do I have a video that goes over? Okay. Yes and no. If you have a NumWorks calculator, which is the greatest calculator in the world, I don't have a video that goes over all of them, even though I think it's great. I just didn't have enough time to get them all done. But if you have a TI-84, which is what most kids have, I do have videos that go over pretty much every single one of those things you just asked. So let me try to find it. That way I could just share it in the All right, I'm back. Sorry. Terrible time to have an internet problem. I feel like I have the best internet in the world. I have no idea what happened. So I'm so sorry if I lost some of you guys, but hopefully we're all back. All right, so I'm trying to find that video playlist for calculators. Let me see if I can get it real quick here. I'm so sorry. All right, here we go. Calculators. Oh, man, I'm so sorry. I should be way more prepared. All right, here it is. Here it is. Here's the playlist. I'm going to share it right now. Here's the playlist. All right, there. I just shared the playlist that has the all the videos that goes over all the different calculator procedures. So sorry that took so long and my internet went out. Thank you guys very much. Sorry. All right, next question. What do we got? Can you explain R and R squared? Yeah. So R is called correlation. Correlation measures the direction, the strength, and the form of a linear relationship, right? So correlation can be positive. It can be negative. Positive means your relationship is going up. Negative means your relationship is going down. Closer to 1 means the stronger the relationship. Closer to -1, the stronger the relationship. Just negative relationship. Closer to 0 in the middle, the weaker the relationship. But it also has to be linear. Like you would never use correlation if it's not linear, right? You got to have a linear relationship. If you see a giant curve, you wouldn't use correlation. Now, you can maybe calculate a correlation because a correlation is a formula. You'll get something, but you wouldn't ever use it. R squared is literally R squared. It's called the coefficient of determination. I've seen this almost every single year, whether it be a multiple choice question or a free response question, wants you to interpret the correlation, the correlation of determination. So R squared, here's the script for it. It's the percentage of variation in the Y variable that is explained by the variation in the X variable. So you just got to fill in the context, right? So let's say you have a scatter plot that shows as the temperature goes up, ice cream sales go up. So the R squared is maybe 89%. You'd say 89% of the variation in ice cream sales is actually because of the variation in temperature. So, that's showing that there's a strong connection between temperature and ice cream sales. So hopefully that makes sense. All right, next question. How do you find the expected counts on a GOF test without ratios provided? Okay. They will give them to you. So if they're going to expect you to use ratios, they will tell you, hey, there's supposed to be 10% green fish. There's supposed to be 30% blue fish. There's supposed to be 5% red. Then you use those proportions to get your expected values. Now, you're implying that there could be a problem where they don't do that. They will do that, I promise, unless the problem says, hey, they're supposed to be equal. So you need to know, well, hey, if there's 5 different colors of fish, 20%, 20%, 20%, 20%, 20%. They're not going to tell you 20%. They're saying equal. With 5 categories, equal means 20%. If there's 4, 25, 25, 25, 25. If there's, whatever, you get the point. So they will tell you what proportions to use, or they will tell you that they're all supposed to be equal. Other than that, they're never going to give you a problem where you have to figure it out on your own. All right, next question. Do you have a video for understanding scripts for FRQ conclusions? I'm assuming you mean inference conclusions. Okay, so the answer to that is yes, kind of. So yes, kind of. So I also have a product called the Ultimate Review Packet and the Ultimate Exam Slayer. And I'm going to show you real quick. Here is the website that gets you to these 2 products. Now, the 2 products are awesome. They're great, but they do cost money. But both of them have a free trial. And in that free trial, both of them, Ultimate Exam Slayer or Ultimate Review Packet, you can get both of them here. But again, you don't have to pay for them if you don't want to. But in them is a ton of free resources. All you have to do is sign up. You get them for free. And if you get the free resources, I have a page for every single test interval there is. 2 sample, 1 sample, interval test, z-test, t-test. I have a reference guide for each of those, and it walks you through everything that you need to have for that particular test. And it does give a little script about how to make the conclusion. Then there's also a free document called, I call it the Bible of Inference, but it's called the Book of Inference. It is it's not a real book, it's a PDF, and it gives you an example of every single type of inference procedure, whether it be an interval, a test, chi-squared, independence, homogeneity, goodness of fit, gives you an example of each of them, and it walks you through how to solve them and what to say and when to say it. So I think that's kind of what you're looking for. So instead of me literally going over them all right now, which would take forever, if you go to that website right there, ultimatereviewpacket.com, even if you just go to ultimatereviewpacket.com and click on statistics, you'll get a link. If you want to purchase them, feel free. I know the test is tomorrow, so if you're looking to stay up all night tonight and practice, the Ultimate Exam Slayer is your best deal because it's got tons of practice questions. But completely for free, don't have to pay for it, is those reference materials that you can use as well. Hi, next question. No. Does an observational study imply correlation? No. Correlation is only used for a linear relationship between 2 quantitative variables. They have to both be number-based, quantitative. An observational study, you can say, oh, I noticed there's a relationship between what kids watch, what type of TV shows they watch, and their behavior. None of that is quantitative. What TV shows they watch, cartoons, live action, anime, action, violent cartoons, violent TV, whatever. That's all categorical. And then how do kids behave? Do they behave good? Do they behave nice? Do they behave bad? Do they get in fights? Are they bullies? Those are all categorical. So again, that's an observational study. Like maybe, oh, a kid watches violent TV, they're going to act violently at school. That's an observational study, but you would never say correlation there because those aren't even quantitative variables. So I think the word you meant there, I think, is causation. Okay, not correlation. You think you meant causation. Causation means that one thing causes another. Now, that can be quantitative or categorical. So, does an observational study imply causation? No. You cannot say that X causes Y because you saw it in an observational study. Absolutely not. But in an experiment, you can. As long as in the experiment you have random assignment, these 50 get this, these 50 get that, then you can actually say, hey, I noticed that if you use this pill, it will cause you to lose weight because that's what I concluded at the end. So hopefully I answered that question right there. Can I go over regression and residuals? Yes. Now, again, I got tons of videos that go over it as well. If you just go to my YouTube channel and in the little magnifying box on my channel, you can enter in like regression, or it's also unit 2. Anything in unit 2 is going to cause this. But I can try to go over as much as I can. So let me share my screen again to just kind of talk about this. I think it'll help. One of these days I'll get better at this when I share my screen. It'll be a lot faster. Right now I'm just super slow. Okay, so let's just say that you have a scatter plot and it looks like this, right? And you say, oh my gosh, I noticed that as X goes up, Y goes up, very strong, positive, linear. It looks like a line. That's great. Now, the next thing, the most logical thing to do is to, put a line through it. That's called our least squares regression line. So there's our line that goes through it. Okay, great. Now, every one of these points, let me just kind of emphasize one. This point right here is going to have what's called a residual value. The residual value is the actual Y minus the predicted Y. So it's this distance right here, the actual distance. Here's the predicted value from the line. Here's the actual value. The distance between them is your residual. So one thing we want to do when we make a least squares regression line, we're trying to go through the data and balance out all the residuals. We don't want all of them big. We don't want all of them too small. We want some positive. We want some negative because we want to go through the data. And when you go through the data, some are positive, some are negative. So when we make what's called a residual plot, we're thinking about those residual values. So this middle line here is 0, and a good residual plot shows nothing. It should show positive and negative residuals throughout. That's a good thing. That means that a linear line went through your data, because when you go through your data, you're going to have residuals above your line, you're going to have points below your line, and some are going to be close to your line, and some are going to naturally be a little bit further away, which is why a residual plot should show no pattern whatsoever. That's an indicator that your linear model was appropriate. If there is a pattern in your residual plot, it means that you probably had a curve in your original data. Okay, next up. What is the most important interpretations to have memorized? Boy, obviously a p-value is important for multiple choice, but being able to make the proper conclusion, if your p-value is below alpha, you reject the null. What does that mean? It means that there is evidence to go with the alternative hypothesis. Obviously, you want to add context to that. If your p-value is above your alpha, you're going to fail to reject the null. There is not enough evidence to go with the alternative hypothesis. We never accept the null. So those are really important. R squared, I mentioned earlier, is another interpretation that comes up a lot. S, the standard deviation of your residuals, is the typical distance that what you're typically off by when you use a least squares regression line. Every time you use a least squares regression line, you're making predictions. You're not going to be perfect. So what are you typically off by? That's your S value. So I would say those are probably some of the most important ones for sure. All right, what else? Replication equals random assignment, enough sample size. Yes, so replication is the more samples, right? The more people you have. So if you're doing an experiment and you just have 3 people taking pill A and 3 people taking pill B, 3 people is it's just too few people. There could be so many differences between these people that those differences could be what is causing the issue, not what we're giving them. So, but if we have 300 people versus 300 people, and these 300 people all get better than these 300 people, well, that's replication. That's going to give us stronger evidence to support our conclusion. But also we need the random assignment, right? Because what random assignment does is it makes these two groups similar. The whole point of the experiment is that I want group A and group B to be as similar as possible. And what I mean by that is I want them to be different within. I want this group to be nice and mixed up. I want this group to be nice and mixed up. If they're both nice and mixed up, they're very similar other than what I give them. These guys got A, these guys got B. And now all of a sudden, because they're so similar and because there were so many of them, that's the replication, then I'm going to have really good conclusions, really good evidence at the end. All right, what else? There truly is no official minimal number of people. What matters way more is that you have that you have a good random sample, right? If you have a sample of 500, that sounds great. But if it's a poorly selected sample, it's bad. So you're never going to be tested over a specific number of what a good sample is. There really is an answer there. All right, let's see here. We're over an hour, so let's try to do a little bit more, and then I got to go. Sorry. What is center and spread in SOCs? So SOCS is an acronym that a lot of teachers use. So when you see a histogram or a dot plot or a box plot, you want to describe it. You want to tell me what you see. So we talk about shape, skewed left, skewed right, binomial, bimodal, unimodal, symmetric. Those are shape. The other S stands for spread. Is your data like clumped together between 10 and 20, or is your data spread from 90 to 1,000, whatever, right? How spread out is your data? Center is, C stands for center. Now, officially, right, there's the mean and the median, but when you're just describing a histogram, don't talk about the mean and median. Unless you're asked to. If you're asked to, you asked to, right? Talk about it if you're asked to. But if you're just saying, what's the center, just look at it and be like, looks to be around 60. 60 is about a good center, right? You're just eyeballing it to what you think a good center is. And then obviously outliers, if you see a value that's really far away from all the others, you're going to talk about an outlier. But if you just have a histogram and you say, hey, describe the histogram, describe the distribution, very generic, right? Talk in context, but don't overspeak. Just talk about shape, center, spread, and outliers. The other reason why I got to go soon, I'm losing my voice talking so much. All right, what else? If you can do a calculation on the calculator, do you have to show the manual process on FRQs? Okay. If it's a test for inference or conference interval, you don't have to show really any work. As long as you follow, again, that video I was talking about where I talk about panic and phantom, my acronyms for what you need for an interval or a test. No, you don't have to show formulas. If you name it properly, your calculator will give you a p-value. Your calculator will give you your test statistic, your z-score, t-score. Write them down. Use the p-value to make your conclusion. You're good to go. You don't have to show formulas. Now, if it's a probability-based question and it's binomial, you need to show the work. You could use the calculator to do the work. That way you know it's right and it's quick. But you got to show some work in terms of how you got it. Now, if you're saying, hey, I'm going to write binomial PDF, I'm going to say, here's what n represents, here's what x represents, here's what p represents, that's fine too. That works. Or if you're going to use normal CDF, I just like saying, hey, listen, here's what I'm trying to find the probability of. I got the z-score, and I'm going to use normal CDF to find my z-score. But yes, if you label everything, you should be fine. So hopefully I answered that question. Sorry, kind of quickly there. All right, what else? Okay, so I explained power earlier. Maybe you just weren't in the chat, which is totally fine, Jules. But power is the probability of correctly identifying a true alternative. So what are we supposed to do when we correctly reject the null? Okay, so when in a test, you have a low p-value, you reject the null. You might be wrong. You might have done something wrong, right? You might have made a type 1 error. The null was true, but you rejected it. You didn't know that. So if we knew the truth, we would never do the test. Like if we knew that more than 25% of people recycled, we want to do a test to figure out if more than 25 people recycled. We know the truth. So what I'm trying to get at is you're never going to know the result. You're never going to know the truth. You're making a conclusion based on your p-value. There's always a chance it's wrong. It's all hypothetical. So power is simply the idea that if the alternative is true, we want to conclude that. And power is the probability that you do conclude that properly. So what are we supposed to do when we correctly reject the null? Well, nothing. If you correctly reject the null, because that's what was supposed to be true, because maybe you find out afterwards, hey, you were right, that was the truth. Well, then that you had power and you did the right thing. All right, what else? Teddy Goodman, that sounds familiar. How does the procedure affect the degrees of freedom, e.g. slope t-test? Okay, great question, Teddy. Oh my God, Teddy, you must be just so smart. So if you're working with a one sample t-test or a one sample t-interval, the degrees of freedom formula is the easiest form in the entire world, sample size -1. Unbelievable. If you're working with a test for slope, interval, or test, the degrees of freedom for slope is sample size -2. Because with slope, there are two variables, the x and the y, so sample size -2. If it's a two sample t-test for the difference between two sample means, or an interval for the difference between two sample means, the formula for degrees of freedom is ugly. Now, if you use your calculator, it will give you the correct degrees of freedom. It's like a decimal. That's great if you use your calculator. But if you don't want to use your calculator, the degrees of freedom formula, you don't want to use it. So just don't use it. It's not even in the curriculum. Don't worry about it. What we do is we use one of two options. It's an estimate. It works just good enough. It's totally fine for the AP exam. There's two things you can do. You take the degrees of freedom for each sample. So let's say you have a sample of 10, a sample of 20. So you got 9 and 19. You could use the smaller of the two. So you use 9 degrees of freedom. It's not right, but it's what you use. Or you could take the 9 and 19, add them together, and use that for your degrees of freedom. Both of them are technically wrong because the formula for degrees of freedom for two samples is very confusing. Don't worry about it. If you use your calculator, it will give it to you correctly. So Teddy, hopefully I answered that question correctly. What wait, is this Ogama be posted or available when live ends? You gonna? I don't know what that means. Yes, I believe that when I end this, it will stay on my channel. It'll either be at the top, or if you go to my content, there should be a tab for live, and it would be under there. So it should stay. Yes, I'm not going to delete it. All right, I got about 5 more minutes in me. Can you explain how sampling and population distributions work? We'll go back to that last one, Patrick. Or did we not want to do that one? Okay, let me talk about this real quick. So a population distribution is the distribution of a population, right? Every rhinoceros in the entire world, what is their weight, right? Maybe we see it skewed right, where there's lots of lower weight rhinoceroses and very, very few very, very high weight rhinoceroses. Okay, whatever. But it's just literally showing the entire population of all rhinoceroses. A sampling distribution is not showing all of them. It's showing sample means. So if we get a sample of 50 rhinoceroses, we get a mean from that sample, and we get another sample of 50, another sample of 50, another sample of 50, another sample of 50. And that's what central limit theorem tells us, that even if that population was skewed right, when we start looking at samples of size 50 and we look at the mean of those samples, the sampling distribution is going to be normal, because we're not looking at the population, we're not looking at individuals, we're looking at the mean of a sample, and that will become normal. All right, next one. Does raising sigma or lowering sigma also increase power? Do you mean alpha? I think you mean alpha. When you say sigma, sigma is the standard deviation of the population, which you're not going to know. So I think you mean alpha. Yes, alpha does affect power. If you increase alpha, your significance level, you will increase your power, because you give yourself more room to reject. And if you're supposed to reject, then you have more power. What else? If you go from a one-sided test to a two-sided, what happens to the p-value? It doubles. So if you have a one-sided test and you go to a two-sided test, your p-value simply doubles. That easy. Because one side only looks at one side, and a two-side says, well, hey, there could be a similar one on the other side, but because of symmetry, they're the same, so that's why it just doubles. What else? Okay, so great question, Alicia, no, I say shit. Great question. So if you are working with a single thing, like you're just looking for a population proportion or a population mean, you'd say, hey, I'm 95% confident that the true proportion of sea fans in the Atlantic Ocean that are infected with a disease is somewhere between 18 and 23%. Bingo, easy, right? But if it's mean, say, hey, I'm 99% confident that the true mean weight of all rhinoceroses is somewhere between 1,042 pounds and 1,057 pounds, whatever. But if it's a difference between two, then you want to make sure that you compare. So maybe you're working with an interval and you say, hey, I'm looking at the difference between the proportion of girls that like chocolate ice cream and the proportion of boys that like chocolate ice cream. You say, hey, I'm 95% confident that the proportion of girls is anywhere from 10% higher to 2% lower, because maybe one side of your interval was positive 10%, the other side was negative, and a negative would mean that the girls were lower. So you'd say I'm 95% confident the proportion of girls is anywhere from 10% higher to 2% lower than the proportion of boys that like chocolate ice cream. So hopefully I answered that one. Good question. Really good question. And again, if you watch that video, I talk about that panic and phantom, that video for inference procedures, I do go over that. All right, a couple more. Before you end, can you give an FRQ predictions for funsies? Of course, Dom. Okay, so I think that the first question is going to deal with some type of data display. I'm going to go with the box plot this year. So you're going to give it a box plot. You're going to be asked something about the box plot, maybe identify the median, the IQR, maybe identify outliers. And then you're going to be asked about, hey, is the mean higher or lower? Well, if you're skewed right, the mean is going to be higher than the median. If you're skewed left, the mean is going to be lower. Something along those lines. I think the second question is going to be a problem that deals with an experiment. So it's going to describe an experiment. It's going to ask you about the treatments, the experimental units. It's going to ask you to describe how they are going to do the randomization process. and then maybe a question about replication, the importance of replication, single blind, double blind, something along those lines. I think the third question is going to be an inference-based question. I'm going to go with a confidence interval for the difference between two population means. That's what I'm going to go with. Haven't seen that one in a long time. I think the fourth question is going to be probability-based. And they did binomial and geometric last year. I would love to see it again because if you know binomial, I think it's easy. But I think it's going to be a probability-based question based on a sampling distribution. So you're going to create a sampling distribution, and you're going to be asked to find the probabilities of certain sample outcomes. And then the fifth question is going to be a multi-focus question. I'm thinking maybe a scatter plot, something to do with linear regression, interpreting slope, interpreting y-intercept. And then the sixth one, I have no idea. I can't even begin to guess for the investigate task. All right, that is it. I know there's plenty more comments. I'm sorry if I didn't get to everybody, but can I give you a pep talk? Yeah, honestly, guys, the number one thing I tell my students, they probably hate me. I think they like me. I don't know. But you don't have to do good to do good. So don't go in spazzing out like, I got to get every question right. I want to get a perfect 100%. It's just not going to be possible. So just take your time, do the questions that you know how to do. The ones that you get stuck on, go back, try them again. And I think you'll do okay. But if you get a 60%, like that's terrible, right? You would think that's terrible, right? Nobody wants a 60% in the grade book. But at the same time, that's going to be good enough to get you a 5. Like, come on, seriously. So you don't have to do good to do good. You guys are all going to do great. Don't you dare say you're cooked. If you've been watching my videos, I think you're going to be just fine because, it's honestly, right? It's a confounding variable. Watching my videos, yeah, it's going to help you learn, but it's the fact that you care enough to watch my videos, to try to learn. You already have that desire and that care, and that's why you're going to get a 5. It's not because of my videos. It's because you care. And Teddy, thanks, buddy. You are the GOAT as well. I honestly, Teddy, I can only imagine that Cooper's not watching this video. He's probably sleeping or something or talking to his girlfriend on the phone. It's a shame. All right, that's it. Appreciate everybody. Thank you so much. If I didn't answer your question, I guarantee I have a video that will answer it. So all you got to do is check it out and find my videos. All right. See you, everybody. Thank you.